Today we are happy to have Bendeguz Offertaler. Sorry if I pronounce your name incorrectly. And he's going to speak about chaos and the reparametrization mode on the AdS2 string. So please, you're welcome to start.
Thank you. Thank you very much for the introduction and also for the invitation to talk about our work. Today I'm going to talk about this work from the end of last year in collaboration with my advisor, Simone Giombi, and with Shota Komatsu, who's at CERN. So I will begin with a few slides of background, briefly reviewing the correspondence between Wilson loops and strings in AdS-CFT, and then introducing the setup of our analysis. Wilson loops are fundamental observables in any gauge theory. They play an important role in QCD because they are the order parameter for confinement. And in a confining theory, Wilson loops obey the area law, which corresponds to a quark-antiquark potential that grows linearly with the distance. By contrast, in a conformal theory, the Wilson loop can only depend on the shape, not the size of the contour. So the quark-antiquark potential goes like 1 over the distance. The intuitive interpretation for the area law in a confining theory is that the flux lines collimate and form an effective string connecting the quark and antiquark. The area law is realized precisely in AdS-CFT, but in a way that is compatible with the conformality of the gauge theory. This is possible because the string that the quark and antiquark are connected by lives in a higher dimensional anti de Sitter space rather than the same space as the gauge theory. My focus today will be on Wilson loops in n=4 super Yang-Mills, which is a very special gauge theory that is exactly conformal, has maximal supersymmetry, and many other nice properties. And the Wilson loops we will consider are a variant of the ordinary Wilson loop. In this variant, sometimes called the Maldacena-Wilson loop, in addition to the gauge fields coupling to some space-time contour x mu, the scalars in the theory couple to some contour theta I in an internal S5 space. One advantage of studying this class of Wilson loops is that for smooth contours, they are locally supersymmetric, which protects them from renormalization. And in addition, for suitably symmetric choices of the contours x mu and theta I, the Wilson loop is globally supersymmetric and is often amenable to exact computations. In AdS-CFT, n=4 super Yang-Mills is dual to a string theory in AdS5 Cross S5, and these Maldacena-Wilson loops are dual to open strings that are incident on the contour x mu and theta I on the boundary. So the Wilson loop expectation value is identified with the string partition function, which in the supergravity regime is just given by the classical string action. So the classical string forms a minimal surface, and this is the holographic area law. The most famous example is the half BPS Wilson loop, where the space-time contour is just a circle, and the contour on S5 is just a point. This object preserves half of the supersymmetry. And its computation on both sides of the correspondence was one of the early checks of the AdS-CFT correspondence. On the gauge theory side, Eriksson, Semenoff, and Zarembo first computed the expectation value by summing up non-interacting diagrams, which for this choice of contour is just constant. And so the calculation reduces to a finite dimensional matrix integral. Pestun later proved using supersymmetric localization that the Wilson loop expectation value indeed reduces to this matrix integral. As a result, the expectation value is known for any value of the gauge group rank M and the Yang-Mills coupling G. And the planar limit is given by this Bessel function, which at strong coupling takes this simple form. We can compare the gauge theory result with the prediction from AdS-CFT. The minimal surface incident on a circular contour on the boundary is just a hemisphere whose worldsheet geometry is AdS2. The area takes this form. Here R is the size of the circular contour, and epsilon is cut off into bulk. So this first term is divergent, and we interpret it as renormalizing the mass of the propagating quark. Alternatively, we can more precisely add a boundary term to the action that makes the total action finite. Either way, the renormalized area is minus 2 pi, and the string partition function in the strong coupling regime, in the supergravity regime, is given by e to the root lambda in agreement with the gauge theory result. Let me also say that the Wilson operator with a straight line contour is also half BPS, and the line and circle are related by a conformal transformation, but their expectation values are not the same due to a conformal anomaly. But for the purposes of this talk, we can, as we'll see in a bit, we can treat the two interchangeably. Another motivation for studying the half VPS Wilson loop is that it is a quintessential example of a conformal defect. Defects in QFT are operators with support on some submanifold in space-time, and they have been studied a lot in a variety of contexts. In a CFT, one can also in particular study conformal defects, which are defects that preserve a smaller conformal group that is a subgroup of the conformal symmetry of the parent theory. One can then, for instance, consider operators inserted on the defect or in the bulk, as well as their interplay. And if we restrict our attention to operators just on the defect, then we can think of it as a lower dimensional CFT. So just in this way, the Wilson line or Wilson loop defines a one-dimensional conformal defect. In particular, it breaks the superconformal group of n equals 4 super Yang mills to a 1D superconformal group, which includes, in addition to the 16 fermionic generators, the bosonic subgroup SL2R cross SO3 cross SO5. Here, SO3 are the rotations in space-time around the Wilson line. SO5 are rotations of the 5 scalars that don't couple to the Wilson line. And SL2R is the 1D group of 1D conformal transformations that act on the line, which includes the dilations, translations, and superconformal transformations. We can define defect correlators of adjoint operators by inserting them along the contour and connecting them with in path order and connecting them with sections of the Wilson line to create this gauge invariant operator. Once we normalize by the expectation value of the Wilson line or the circle, then these defect correlators on the line and circle are related by a conformal transformation, which is why we can treat them interchangeably. Such defect correlators arise naturally when considering small fluctuations of the contour. For example, small fluctuations of the space-time contour in the 3 transverse directions pull down insertions of the displacement, the so-called displacement operator. And fluctuations of the contour in S5 inserts the 5 scalar operators that do not couple to the Wilson line, the half BPS Wilson line. And these displacement operators and scalar operators inserted along the Wilson line are dual to transverse fluctuations of this half BPS, sorry, the AdS2 string in AdS5, and the 5 transverse fluctuations in S5. The defect correlators are constrained by 1D conformal symmetry, just like in higher dimensional CFT. For example, operators can be classified as primaries and descendants, with the primaries being labeled by a scaling dimension under SL2R, and also the representation under SO3 cross SO5. So for example, the SL2R fixes in the usual way the 2 and 3 point functions to take this familiar form, and also fixes the 4 point functions to a function of a single conformally invariant cross ratio chi. And in 1 dimensions, there is only one independent cross ratio. Finally, before I get into the specific observables that we were studying in this most recent work, let me just mention that this defect CFT setup has been studied extensively using a variety of techniques, and the system has proven to be a very interesting playground for studying the intersections of various non-perturbative techniques. So in this talk, we're going to restrict our focus to certain 4-point functions in the Wilson line defect CFT at strong coupling and in the planar limit. And we'll focus on just, for the most part, on just correlators of a single scalar. In terms of the dual string, this corresponds to considering weakly interacting fluctuations of the string in an AdS2 Cross S1 subspace of AdS5 Cross S5. So here S1 is just one of the angular directions in S5. We'll work with Poincare coordinates x and z on AdS2 and polar coordinates on S1 so that the metric takes this form. The string is incident on some curve on the boundary of AdS2 Cross S1, which we will parametrize by the AdS2 boundary coordinate x, and by this function y tilde of x, which tells us how much the string fluctuates in the S1 direction. And the unperturbed AdS2 string, which is dual to the Wilson line without fluctuations of the contour, corresponds to y tilde equals y equals 0. So the scalar 4-point functions, which we can also write as with this notation, which we read as defect correlators, boundary correlators for the transverse directions of the string, are just given by taking variational derivatives of the string partition function with respect to this function y tilde. Let me also note that although our motivation is to better understand the Wilson line defect CFT, as long as we are computing these correlators in the supergravity approximation, then we are essentially just studying minimal surfaces in AdS2 Cross S1. Okay, to get some better understanding of these correlators, let me review how they are computed at strong coupling in the static gauge following this paper. So in static gauge, we identify the string worldsheet coordinates T and S with the AdS2 bulk coordinates x and z. So the AdS2 coordinates are non-dynamical, and only the transverse coordinate y is dynamical. The string action is just an Nabu-Goto action with this boundary condition for the transverse coordinate. Correlators with a few insertions, few operators, correspond to small fluctuations of the boundary curve from a straight line. And so y tilde is, we can treat y tilde as being small. And if the string tension is also large, because we're at strong coupling, then the corresponding fluctuations on the string y will also be small. So this means that we can expand the action in powers of y. These are the first three terms. The leading term just gives us the divergence for the worldsheet area that we saw before, that we interpret as renormalized into quark mass, so we drop it. The next two terms, the other terms tell us that the transverse coordinates are massless. The transverse coordinate is a massless field in AdS2 with a tower of interactions, the lowest interaction of which is this 4-point 4-derivative vertex. So in order to compute correlators, boundary correlators on the string, we just compute Witten diagrams in AdS2 with these possible interactions. So for example, the leading contribution to the 4-point function at strong coupling is given by contracting the 4 boundary points with boundary to boundary propagators, which are just the conformal 2-point function 1 over x squared. The leading interacting Witten diagram is this 4-point contact diagram, where there are 4 boundary to bulk propagators contracted with the 4-derivative interaction vertex, and the bulk point is integrated over AdS2. In higher dimensional CFTs, higher dimensional ADS, these integrated contact diagrams give rise to the so-called D functions. But in AdS2, they are especially simple, and they reduce to logarithms. So we find that the normalized 4-point function takes this form with this explicit expression for the free and tree level contributions. We see that, as expected, the correlator is just a function of the single conformal invariant cross ratio chi. And the tree level is suppressed by 1 over the string tension. If we wanted to compute higher order contributions at higher orders in 1 over the string tension, we would have to include loop diagrams, schematically shown here. So the field that runs in this loop would now we would have to include the contributions of all the matter fields, including the fermionic coordinates that we have been neglecting so far, and we will neglect. And once we start computing loop diagrams, that corresponds to going beyond the supergravity approximation, beyond just studying minimal surfaces in AdS2 Cross S1. Okay, so now we're going to take these 4-point functions on the string and put them into out-of-time order configurations. Perhaps I should pause and ask if there are any questions so far about the background and the setup. Okay, so let me begin by briefly reviewing out-of-time order correlators. They are simple diagnostics of quantum chaos and have received a lot of attention in recent years, especially in holographic settings. One way to motivate the study of the OTOC is that the defining feature of a classically chaotic system is that two systems with nearly identical initial conditions diverge exponentially in time, in phase space. One way to quantify this is to introduce the Lyapunov exponent, which determines the rate of exponential divergence, which we can define as this phase space expectation value of the derivative of the position at time t with respect to the derivative at the position with respect to the position at time 0. And this derivative is just a Poisson bracket of q of t and p of 0. So a natural generalization for a quantum system is to consider the thermal expectation value of the commutator of two operators v and w, one at time 0 and one at time t. In a semi-classical chaotic system, we expect this OTOC to grow exponentially. And the exponential growth is driven by the out-of-time order terms, which take this form. So here, lambda sub L is our quantum Lyapunov exponent. And epsilon is some semi-classical small parameter. Like, for instance, it could be h bar. In our setting, it's 1 over the string tension. We can visualize the OTOC by drawing the integration contour on the thermal cylinder. So here, real or Lorentzian time goes to the right, and imaginary Euclidean time goes down, and it's periodic. This first section of the contour gives the Euclidean evolution, which produces this Boltzmann factor in the expectation value. And these folds to the right give the Lorentzian evolution of the W operators. More generally, it's often convenient to separate the V and W operators in the Euclidean time direction, partly as a regulator. So a simple choice is to space them equally around the thermal circle. And OTOCs with different spacings will have slightly different properties and interpretations, but their qualitative behavior will be similar. Another important property of the OTOCs is that the Lyapunov exponent satisfies a bound, which follows from the analyticity and boundedness properties of the OTOC. And in particular, Einstein gravity saturates this bound. So we were interested in studying OTOCs in the Wilson line defect CFT, or in other words, on the boundary of the open string. So we computed the OTOCs by taking our Euclidean 4-point functions and analytically continuing them into this out-of-time order configuration. So if we start with our correlators on the line, we can map it with a conformal transformation to the circle, and then we can put the 4 operators, space them equally around the circle, and then analytically continue 2 antipodal operators to Lorentzian time t. So we computed the static gauge. No, so we saw previously the result for the 4-point function of static gauge. I just reproduced the relevant terms for the computation of the OTOC.
Could you explain what is beta in this setting? So previously it was a temperature. So here, what's the meaning of this Euclidean? Circle?
Right. So beta from in terms of the Euclidean correlators is the circumference of the circle. Right. We will see in a second when we interpret these correlators in terms of scattering amplitudes that the temperature can be thought of as the UNU temperature for the accelerating quark and anti-quark pair that the string is incident on. Maybe I should say that. Maybe I'll leave it at that.
So once again, we were on the line originally. So you insert some operator on the line, you get Euclidean correlator. So I'm lost. So I can understand you can continue this one dimension into Minkowski get time, but only where is Euclidean time. Well, maybe we're postponing this. Maybe it will become clearer later.
Okay. Yeah. Maybe it'll become a little bit clearer later. So let's take these this configuration for the 4 operators on the circle, on the Euclidean circle. This corresponds to this conformally invariant cross ratio as a function of the Lorentzian time t. And doing the analytic continuation, the logarithm just picks up non-zero monodromy, and this 1/chi gives us an exponentially growing piece. So the correlator takes this form, and in particular, we see that if we're setting beta to be 2π, which means that we're starting with a unit radius circular contour, then this saturates the chaos bound, which was also observed by these authors using slightly different arguments that we will kind of get to in a bit. Okay, so the tree level result for the OTOC in static gauge is enough to see this maximal chaos on the string, enough to see that the Lyapunov exponent saturates the chaos bound. But once the time is of order the logarithm of the string tension, then the first 2 terms in the correlator are not reliable. It would be interesting to consider how the OTOC behaves around that scrambling time. So naively, this would require that we compute higher order corrections by computing loop diagrams. But luckily for us, Ferrero and Meneghelli were able to determine an analytic result for the 4-point function on the Wilson loop defect CFT, essentially by taking the tree level results and providing a suitable ansatz for the 1, 2, and 3 loop contributions, and then fixing them by imposing the bootstrap crossing equation and with some extra cleverness. So we'll simply take the result and see what it tells us about the higher order contributions to the OTOC. So the general expression for the exact correlator is complicated, but if we're only interested in the terms that are growing fastest in time at each order in the strong coupling expansion, then these are the only terms that contribute. And if we do the analytic continuation, taking the time t and the string tension to be infinity with this ratio held fixed, then we get the first few terms in a series expansion, which we identify as the series expansion of the confluent hypergeometric function, which is just a particular special function. We can plot the recent results for the OTOC as a function of time, and we see that it interpolates smoothly between this initial region with Lyapunov growth and this exponentially decaying region. It's also interesting to note that the result for the OTOC is the same as in JT gravity, which is a toy model of 2D gravity that has received a lot of attention in recent years. So this result for the double-scaled OTOC, based on the bootstrapped result by Ferrero and Meneghelli, and also this observation that the result for the double-scaled OTOC is the same as in JT gravity, was essentially the starting point of our project. So the puzzle that we want.
Could you please explain one thing?
Yes.
So usually when one discusses correlators in the CFT, they have some kind of power series expansion, right? Or like with conformal dimensions, like you can do, let's say, like OPE.
Right.
So I don't understand how this story matches with this expansion that you have, in which you have some exponent of T.
So like T being the position between the
Yeah, right. So here, like the first operator is at 0, right? And the second one is at T. So like T goes to 0 is something like S channel limit or something like that, right?
Right. I understand. So this notation is probably misleading. This isn't. So these aren't like the position 0 and position T along the line, for instance. Instead, this time is the Lorentzian time. So the positions of the 4 operators. So if we started with the line and the map to the Euclidean circle, then we could put the operators at 4 points on the circle. And if we brought 2 of the operators close together, that would be like taking the OP limit on the circle. But now, instead of just considering a Euclidean configuration, we are analytically continuing 2 of the operators in the Lorentzian direction. And that is the time T that is labeling these correlators.
Okay, and if you like analytically continue this back, what kind of analytic structure you would see there? I mean, what was the signature of this exponent T? Yeah.
Sorry. What do you mean by signature?
I mean, how does it manifest itself? So can you see this exponent without analytically continuing to the Euclidean signature?
From Euclidean to Lorentzian, I'm not sure.
Or is it a feature like of a general CFT or only of this theory?
No, yes. I think this is a pretty general behavior for CFTs when you do the analytic continuation of Euclidean correlators to a Lorentzian configuration, an out-of-time order configuration.
Okay, thank you.
Thank you for the question. Okay, yes. So this was our starting point. Right. So the puzzle that we wanted to understand better was
can I also ask what is the
we cannot hear you.
Can I ask Dima, can you hear me?
not
very well.
Okay. So can I still ask what is the limit at large kappa of this exact result? At large T or large kappa?
So this region here?
Is it still the limit?
Sorry. So are you asking what is the large kappa behavior of this function?
Yeah. Is it still does it still saturate the limit, the inequality?
Oh no. So that so the chaos bound you're asking about?
Yeah.
The chaos bound is only relevant for the this region at early times. So it's only as to this this first term here.
Okay, thanks.
Okay, yeah. So the puzzle that we set out to understand better was whether there was a simple derivation of this result for the double-scaled OTOC. In addition, we want to understand better why JT gravity and the AdS2 string had the same OTOC. So famously, JT gravity has a boundary mode that is governed by the Schwarzian action. And it seemed natural to ask whether there was some sort of Schwarzian action for the string that was responsible for this coincidence. And indeed, there were a number of papers that have explored this possibility. And what we ended up finding, and what is essentially the punchline of our work, is that there is a boundary reparametrization mode that appears when we study the string in conformal gauge. And it plays an analogous role to the Schwartzian in the computation of the OTOC. Finally, in the course of trying to better understand this second bullet point, we ended up addressing an orthogonal but also interesting question, which is how to compute string correlators in the conformal gauge. So we saw them in static gauge. In conformal gauge, naively, one might think that the transverse modes are non-interacting and might therefore wonder how there can be non-trivial correlators. But it turns out that the boundary reparametrization mode mediates the interactions of the transverse modes. Okay, so first let me try to review the scattering argument for the scattering derivation of the double-scaled OTOC. So scattering is a Lorentzian phenomenon. So instead of analytically continuing the Euclidean correlators at the end, let's begin by analytically continuing the circular Wilson loop in Euclidean signature to a hyperbolic Wilson loop in hyperbolic Wilson operator in Lorentzian signature. So this plane represents a two-dimensional slice of Minkowski space in which n equals 4 super Yang-Mills lives. And these blue contours are supposed to represent a quark and anti-quark, which are accelerating at a constant acceleration. So in this setup, the original Euclidean time, or angle along the circle, becomes the proper time of the quarks. And also in this setup, if we have acceleration, we take the acceleration to be 1, then the temperature is just 2 pi, which we interpret as the Unruh temperature because the quarks are accelerating. So in the Poincare patch of AdS5, the classical string incident on this pair of contours is a hyperboloid, which is just the Lorentzian continuation of the hemisphere. And it has Lorentzian AdS2 geometry. For discussing the scattering argument, it's useful to introduce some Kruskal light cone coordinates U and V, which cover the entire world sheet. And the world sheet metric takes this form. An important point is that U and V are related exponentially in time, exponentially to the proper time of the quarks. And this essentially reflects the fact that time translations in Rindler space are boosts in Minkowski space. Okay, so now we will interpret the OTOC as a scattering amplitude on this AdS2 geometry. The scattering interpretation of OTOCs was worked out and given a precise prescription by Schenker and Stanford in the context of correlators in a general theory dual to Einstein gravity. It was then adapted by these authors to the worldsheet, and they used it to show the maximal chaos of the string correlators. And I'm now going to review the general argument and then show that it also correctly reproduces the double scaling limit for the OTOC. So for generality, let's consider some operators V and W, which could be the scalars, or they could be more general operators. Let's also put the operators in a more symmetric configuration where W is now at time t over 2, and V is at time minus t over 2. This is Lorentzian time. We put in this symmetric configuration just to make the scattering interpretation more manifest. So then we write this OTOC, this correlator, as an overlap of two states, alpha and beta, which can be interpreted as out states and in states for a scattering process on the AdS2 worldsheet. So to see intuitively why alpha can be interpreted as an out state, let's follow Schenker and Stanford and construct this state step by step. So this is supposed to be a Penrose diagram of the AdS2 worldsheet, which is just the Kruskal diagram with U and V compactified. So we start at t equals 0 with the vacuum state. Then we evolve back in time to minus t over 2 and act with the operator V, which produces some particle near the boundary that will move into the bulk of the AdS2 string. We then evolve forward in time to t over 2 and act with the operator W, which produces a second operator near the boundary. During this evolution from minus t over 2 to t over 2, the particle that was created by V propagates into the bulk of the string from the lower right corner to the top left corner in the Penrose diagram. And since we end up with two particles that are far separated, moving in opposite directions, this is naturally interpreted as an out state. And we can repeat the same step-by-step construction of the beta state and see that it is naturally interpreted as an in state. One point is that since we're going to take t to infinity, v and w act far in the past and far in the future. So the particles that they create move along the v equals 0 and u equals 0 horizons. And they're therefore highly boosted relative to each other. So the scattering interaction we will interpret as being local on the AdS2 string and high energy. So to turn this previous picture into a precise formula for the OTOC, we write the OTOC as some overlap of wave functions for the in and out states with this scattering matrix in Kruskal momentum basis. So the wave functions that we're supposed to take are the are psi and phi are given by Fourier transforms of the bulk boundary propagator. And the S matrix in 2-to-2 scattering in 2 dimensions is diagonal with just a phase shift. And we need to identify what the phase shift should be. And the phase shift that we should use, and that produces the correct result for the double scaling limit of the OTOC, is the phase shift for scattering on the infinitely long string in flat space that was derived by Dubovsky, Flogger, and Gorbenko. The fact that we can apply the flat space phase shift can be interpreted as reflecting the fact that the scattering process on the AdS2 string occurs in a local region. And the phase shift takes this form. The exponent is proportional to the light momenta PU and PV, or in other words, just the Mandelstam center of mass energy S. So when we assemble the ingredients into the integral, we arrive at this sort of expression, which can be evaluated and indeed reproduces the confluent hypergeometric function that we predicted by resumming the Faro-Meneghelli result. So the scattering argument gives a simple, relatively simple physical understanding of the double scaling OTOC. I should also say that this, as I said, this scattering interpretation of the OTOCs in Einstein gravity is very similar to what we just did here, except it's simpler in AdS2 because there are fewer dimensions. And also essentially the same analysis holds for the OTOCs in JT gravity. So one way to understand why the two theories have the same correlator, the same double scaling, same OTOC in the double scaling limit, is that they can both be interpreted as scattering amplitudes on the same background geometry and with the same scattering phase. Okay, maybe I should pause here.
Sorry, do you say that you said that using the scattering argument you managed to reproduce the result that came after like summing over loops before, right?
Yes.
So except that one was exact, and here you use some kind of approximation, replacing some area scattering with flat scattering. So what was the discussion with phase? So I don't quite understand it.
I see. Okay, yes. So let me just say that, right. So essentially, in this scattering understanding, the scattering picture of the OTOC, there is some S matrix that governs the interactions of the particles on the string roll sheet. And the scattering phase that we input is this scattering phase for excitations of the string in flat space. So we kind of put it in by hand, but it appears to give the right answer. And it kind of seems to reflect that in this limit, we take this limit for the OTOC, the scattering interaction is local on the AdS2 string. So we can approximate it as a flat string.
Mm-hmm. And is there any other definition of the CFT except that like defined holographically the way that you did?
Holographically in terms of the Wilson line defect CFT?
Yeah. So this Wilson line CFT. Okay, so this also gives a definition, right?
It does, yes. Although,
yeah, but probably it's not applicable to computations in this limit, right? So it's
right. So we took the Ferraro-Meneghelli result, which they didn't compute loops. They kind of bootstrapped it using the tree level result from the static gauge analysis of the string. And so the correlator up to that order in strong coupling has not been computed from the gauge theory side. But there have been lots of checks of their result. So for example, from the 4-point function, you can extract OPE CFT data, which you can compare with integrability methods, and they agree very nicely. So the Ferraro-Meneghelli result, which was kind of a strong coupling string result with some bootstrapping, has passed a lot of checks.
But still, for some reason, this holographic computation was useful as like a first input step, right? So they used this tree-level result from the bulk side.
Yes, I think so.
Okay, thank you.
Okay, so let me now move to the third part of the talk. So we could take the scattering picture as a satisfactory resolution to our puzzles about the string double-scaled OTOC. But it's also interesting to return to the idea that there's some boundary reparametrization mode that behaves analogously to the Schwarzian and JT that is responsible for the behavior of the OTOC. So let me first give a very quick review of JT gravity to set the stage and also to identify some structures that we might want to see on the AdS2 string. So JT gravity is a toy model of gravity in AdS2. It consists of some dilaton phi, a metric H, and some matter fields, which we will call Y. The theory is almost topological with no propagating gravitational degrees of freedom, except that the dilaton diverges at the boundary. So it is necessary to introduce a boundary curve, a cutoff curve that has non-trivial dynamics. This cutoff curve can be represented or parametrized, specified by the map or the reparametrization from the proper time along the curve to the time, the AdS2 time along the boundary. One finds that the JT gravity action reduces to a boundary term, which is given by the Schwarzian derivative. This almost follows entirely from symmetry because the JT gravity action is supposed to be invariant under the SL2R transformations that act as isometries on AdS2. And the Schwarzian derivative is the object that is SL2R invariant with the fewest number of derivatives. For the matter action, if we take it to be, in the simplest case, a massless scalar minimally coupled to the metric, then it takes this bilocal integral form along the boundary, where here y tilde is like the source for the matter fields. At the level of the partition function, one can integrate out the metric, the dilaton, which acts as a constraint, and the matter fields, which are quadratic, and are simply left with an integral over the distinct boundary curves, which is equivalent to integrating over all reparametrizations modulo the SL2R transformations on the boundary. And so it takes, so the JT partition function takes this form, and correlators are defined by taking variational derivatives with respect to the matter source field on the boundary. And this theory has proven to be a very nice solvable model of toy gravity that has been studied extensively by many, many authors. So returning to the AdS2 string, we were curious to see if the OTOCs could be understood similarly in terms of some sort of boundary mode. But it has long been known in studies of strings in conformal gauge that boundary reparametrization mode naturally appears. So there were a number of papers along these lines for strings in flat space in the 80s, also for strings in AdS slightly more recently. But the appearance of boundary reparametrizations in the study of strings goes all the way back actually to Douglas's work on finding the minimal area of a surface incident on some sort of on some contour in flat space. He arrived at this integral formula where an important role is being played by the reparametrization of the boundary of the curve alpha, which has to be minimized over. We learned about Douglas's integral formula from various papers by Makienko and also by Kruczynski. So I would like to now briefly review the story of the boundary reparametrization mode in conformal gauge, and then explain how it can be used to compute correlators on the string. So we start with the Polyakov action for the bosonic coordinates of the string. Momentarily, for a moment, we'll keep the discussion general, but we will shortly return to the specific case of the AdS2, the string in AdS2 Cross S1. And also, we will first just study the string at classical level. So in the conformal gauge, the first step is to pick world sheet coordinates where the metric is conformally flat. This this allows us to still act with holomorphic transformations on the world sheet coordinates, and we use that freedom to set the boundary to be at s equals 0. This leaves us only with a residual SL2R symmetry on the world sheet coordinates. And then the condition for the string x mu of s and t to be incident on some curve x tilde of lambda is given like so, where here alpha is some general reparametrization of the boundary. And note that we have no more freedom left in coordinate transformations on the world sheet to get rid of alpha. So alpha will become dynamical and play an important role. So once we fix the conformal gauge, we can write down the equations of motion and solve for the world sheet coordinates x mu on shell. They will depend on the boundary condition specified by the function x tilde and also by the boundary reparametrization mode alpha. At this point, alpha is not determined. But we also have to remember that we have to impose the Virasoro constraint, which is just the equation of motion for the metric, and tells us that the stress tensor on the world sheet is 0. This will fix alpha. So this two-step procedure tells us that we can find the classical action, which depends on x tilde, which specifies the boundary curve. We can find it by plugging in the on-shell solutions for the world sheet coordinates, the string coordinates, into the Polyakov action, and then imposing the Virasoro constraint. But it is a rather nice fact that imposing the Virasoro constraint is equivalent to extremizing over the reparametrization mode alpha. I was originally planning to discuss this step in a little bit of detail, but I think I will skip it and maybe return to it if people have questions.
Excuse me, a question. Why do you need to extremize over alpha if your initial action is reparametrization invariant? So so something missing. Okay. So let me repeat. Why do you need to extremize over alpha if your initial action is reparametrization invariant?
Well, one answer is that extremizing alpha imposes the Virasoro constraint. Another answer is that if we don't extremize over alpha, then alpha at this point can be anything. So our string coordinates x mu depend on alpha. So different choices of alpha will give different results for the action.
Okay, I understand. You will have a gauge symmetry in your action for x tilde, right?
Yes.
Okay, thanks.
Okay. So let's return to the case of the AdS2 string in AdS2 Cross S1. So now it is convenient in this setting to decompose the longitudinal modes and the transverse modes into two decoupled actions. So the longitudinal action will take this form, and the transverse action will take this form. And we have also subtracted off an area piece from the longitudinal action to make it finite. The area piece will, again, be divergent, just like we saw in static gauge, but we can renormalize it and forget about it. The boundary conditions for the longitudinal modes, x and z, are just given like so. So they depend on alpha. The boundary conditions for the transverse field y depends on the curve y tilde that specifies our boundary curve, how it moves in the S1 direction, and also depends on the reparametrization alpha. I should say that the reason why we focused on AdS2 Cross S1, the string in AdS2 Cross S1, because we could nicely decouple the longitudinal modes from the transverse modes. It would be interesting to understand more generally if this story with the boundary reparametrization mode in conformal gauge can also be extended more generally to, for instance, the string in AdS3, where the longitudinal mode and the transverse modes can't be decoupled quite as nicely. But we haven't really thought too much about that. But okay, so at this point, at the level of the actions, the two modes, the longitudinal modes and the transverse modes, are decoupled. They're only coupled through their boundary conditions and through the Virasoro constraint. So let's, and we can study the transverse modes and the longitudinal modes separately. So let's start with the transverse modes. So here's the action and the boundary condition. The equation of motion is just the Laplace equation in 2 dimensions. So we can write down the solution in terms of the massless scalar boundary to bulk propagator in AdS2. We can plug it back into the action, and we get this bilocal integral along the boundary. Here are two different representations. The first of which is naively divergent, but can be understood using analytic regularization, and the second of which is manifestly finite. We should note that this transverse action takes a very similar form to the matter action in JT gravity. So that's the first parallel that we notice. Okay, now let's consider the longitudinal action. Here's the action and the boundary conditions. We can write down the equations of motion, which are two coupled nonlinear PDEs that in general we don't know how to solve. So we have to satisfy ourselves with an understanding of some of its general properties and a perturbative analysis. But for the computation of just the 4-point functions, or more generally, correlators with few operators on the boundary of the string, the perturbative analysis is sufficient. So I was originally planning to go through some of the details in getting to the longitudinal action, but I think for the sake of time, I will simply skip over those slides and simply state the final result. So the idea is that we can study this longitudinal action perturbatively around the saddle point. The saddle is given by alpha of t equals t up to SL2R transformations. So we consider a small perturbation by writing alpha as t plus epsilon. And then we can study the longitudinal action to quadratic order in epsilon. So it takes this explicit form, which we can write in two different forms, one using analytic regularization, the other one which is manifestly finite. And we can also write it in Fourier space, which takes this simple form. These actions appeared also in these previous works by Polyakov, Rychkov, Makanko, and Amburin. And let me just make two comments. First of all, at the quadratic order, the longitudinal action is bilocal. And second of all, we can understand this power of 4 in the denominator as essentially being a consequence of scale invariance. because there are 4 powers of length in the numerator and 4 powers of length in the denominator. Okay, so let me discuss, let me skip this, these slides on deriving the longitudinal action. I can come back to them if people have questions. So far, the discussion was on the Poincare half plane, whose boundary is a line. But we can also consider the Poincare disk, whose boundary is a circle. And the analysis is essentially the same. The expressions for the transverse action and longitudinal action are essentially the same, except with Euclidean distances replaced by chordal distances on the circle. One advantage of considering the longitudinal action on the circle is that when we expand this perturbation around the saddle point, epsilon, in a Fourier sum, then we get this expression, and we can clearly identify 3 zero modes, n equals 0 and plus or minus 1. And these correspond to the SL2R gauge transformations on the worldsheet, which should indeed leave the longitudinal action invariant and therefore be 0 modes. Okay, so what we have seen so far is that in the classical approximation, we can write the string partition function as the exponential of the longitudinal action plus the transverse action, which depend on the reparametrization at the boundary alpha, but then we have to extremize over alpha to impose the Virasoro constraint. And again, the classical approximation to the partition function is sufficient to get the leading contributions to the correlators on the string, which in static gauge corresponds to the tree level diagrams. But now we would like to promote this this extremization over alpha to an integral over alpha. And the idea is that we would like to include some quantum corrections. And in doing so, we follow some of these papers. So if we take the string tension to be very large, then we can approximate the integral over reparametrizations at the saddle point, and that just gets us back to this top equation. But we would like to use this reparametrization path integral to include the contributions of some fluctuations. I should say as a disclaimer that this integral over reparametrizations appears very naturally, when gauge fixing the nonlinear sigma model for the string, except that we would also in general have to include fluctuations over the ghosts and all the matter fields, including the fermionic coordinates that we have been neglecting. So this middle expression is only including the contributions of fluctuations of the reparametrization mode and is sweeping a lot of things under the rug. So we don't really expect this integral to be able to give us the correct results for general correlators on the string in general. But if we're lucky, then in certain kinematics, like for instance, the double scaling OTOC, the fluctuations of the reparametrization will be what dominate and what determine the answer. And so we kind of just took this this approach and to see what we would get. So let me first mention how the correlators are represented in this reparametrization path integral. So recall that we insert boundary operators by taking variational derivatives of the partition function with respect to the function y tilde that specifies the shape of the curve. Y tilde only appears in the transverse action. So, and when we take two derivatives, then we pull down essentially this combination, where here alpha is our reparametrization and beta is its inverse. For some reason, the inverse appears naturally. So this is, we can think of as a conformal two-point function. It's essentially just 1 over the chordal distance squared, but dressed by the reparametrization mode beta. The same object appears in computations of correlators in JT gravity, essentially. So, for instance, our 2- and 4-point functions would take this form, where we replace our operators y with the dressed 2-point function, and then we integrate over reparametrizations. And notice that the longitudinal action plays the role of the effective action for the reparametrizations, in analogy with the Schwarzian action in JT gravity. Okay. Okay, an important point for computing these correlators is that we have two SL2R symmetries for the longitudinal action, or more generally for the AdS2 string. One of them is the gauge symmetry that acts on the worldsheet coordinates, which acts on the reparametrization alpha and its inverse like so. This is a gauge symmetry, and we saw that it led to zero modes in the longitudinal action. So in general, it would give rise to divergences in the path integral. So it needs to be gauge fixed. And we just took a very naive approach where we wrote the measure for the reparametrization as this product over the Fourier modes and separated out the zero modes. And our gauge fixing condition was simply to set these SL2R modes to zero and not integrate over them. And we also have this other SL2R symmetry, which acts on the target space AdS2 coordinates. So it physically moves the string around in the space, in the target space. So it's a physical symmetry, and it leads to word identities for the correlators in the reparametrization path integral. So in particular, these word identities are what ensure that our correlators, are properly SL2R invariant as they should be in a one-dimensional defect CFT. And these word identities are what fix the form of the 2- and 3-point functions and the 4-point functions up to a function of one conformal invariant cross ratio. Okay, so to do perturbation theory in the reparametrization path integral, we need two ingredients. First of all, we have these dressed 2-point functions, which we can expand in powers of epsilon, the fluctuation of the reparametrization mode. And we also need the epsilon propagator, which in Fourier space on the circle takes this form. We can, in position space, just sum over the Fourier modes, and we get this simple closed form. Here, A and B are, in general, depend on our gauge fixing condition. So we need these coefficients to drop out of any gauge invariant, the computation of any gauge invariant observable. We can also do the analysis on the line. Okay, so for example, in the computation of the tree-level 4-point function, we simply take our operators, which now I'm calling V and W, and replace them with the dressed 2-point function, expand the dressed 2-point functions in powers of epsilon, and then do contractions with the epsilon propagator. And the end result, the arithmetic is simple, and the end result takes this form. And if we set the scaling dimensions to 1 and sum over the permutations properly, we correctly reproduce the tree-level correlator in static gauge. So what we saw at the beginning of the talk, in static gauge, we can reproduce in conformal gauge. But here, the interactions between the operators are mediated by this reparametrization mode, alpha equals t plus epsilon. Okay, finally, let's try to use this reparametrization path integral to compute the OTOC in the double scaling limit. We will do so out of necessity by keeping only the quadratic action, which corresponds to resumming only a subset of all possible diagrams in which the reparametrization modes are exchanged directly between the dressed 2-point functions. So, right, so the honest computation of the double-scaled OTOC would require computing the loop diagrams at higher orders, which in general is very difficult. The fact that we are truncating to quadratic order in the longitudinal action and forgetting about the fluctuations of anything other than the reparametrization mode is an assumption that we have to make. But summing up this subset of diagrams does kind of have intuitive interpretation or parallel with the iconal approximation in high energy scattering in gravity, where one often can just sum up graviton exchanges between the matter fields. But okay, so let me not go through the details here. The point is that since we're only working with the longitudinal action to quadratic order, we can use Wick's theorem and with some cleverness, we can write the OTOC in this double integral form, which takes precisely the form of the scattering result for the OTOC. Okay, so to conclude, let me just summarize the main messages of the talk. So first of all, we saw that double-scaled OTOC could be understood as a holographic scattering process on the string world sheet, and that this scattering result, this scattering formulation, agrees to 3 loops with the analytic result of Ferraro and Meneghelli for the 4-point function, analytically continue to the out-of-time order configuration. We also studied the correlators in conformal gauge, and we saw that a key role was played by the boundary reparametrization mode, and we're able to use it to rederive the OTOC in the Lyapunov regime, so at the leading strong coupling correction, and also more heuristically in the double scaling limit. And there are some open questions which could be interesting, but let me stop here. And thank you for listening.
Thank you. Are there any questions? Okay, maybe you can explain why this OTOC story is relevant. So to me, like any correlator can be analytically continued everywhere or analytically continued back. So, and what you did, you were essentially computing just, I don't know, like Witten diagrams for, which is also like, it can be done like in any signature, right? And analytically continued to every
Yes, I think so.
signature, yeah. So this chaos and OTOC method.
Right, right. I would say that, right. I think OTOCs are a simple way to study chaos in a general system. Oftentimes the system is very, very complicated, and it's hard to study more robust metrics of chaos. Like for instance, sometimes people talk about the spectral statistics of the Hamiltonian. So the OTOC is a very simple object that one can compute. In our case, in our setting, it's not entirely clear what it implies about chaos. I would say that the OTOC is, in my understanding, and I'm no expert, but the OTOC has some limitations as a diagnostic of chaos. So for example, some chaotic systems don't have a semi-classical parameter, so they don't have this nice Lyapunov regime where you can identify an exponential growth. And on the other hand, there are some systems, I believe, that are integrable that still have that still have exponential growth in the Lyapunov regime. So, and actually the string is almost seems like an example, because the string is supposed to be integrable. The world sheet theory of the string is supposed to be integrable, and n equals first degree Yang-Mills is integrable in planar limit. So it was a little bit puzzling for us that the fact that you have this maximal chaos on the string seems at first to be incompatible with integrability. But I think it's, I'm not entirely sure how to understand that. I think it reflects the limitation of thinking of the OTOC as a measure of chaos. So our main motivation was, we kind of used chaos and OTOC interchangeably in the talk and also in the paper. But really our motivation was just to understand this apparent coincidence with JT gravity. That was our main motivation. Because a lot of people had, some people, understandably, suspected that there was some sort of Schwartzian on the string. Already, just because the OTOC had this maximal chaos, and the fact that the OTOC in the double scaling limit appears to match exactly, one would hint that it's further evidence that that there's a Schwartzian on the string. But we don't find a Schwartzian. We find some other reparametrization action, which serves the same role in the computation of the OTOC. But yeah, really, we just wanted to understand that apparent coincidence.
Okay, thank you.
Can I also ask a question? So in one of the big pictures, you literally have a scattering system. So one of the definitions of chaos is that this is a sensitivity, kind of sensitivity to initial conditions. So why don't you use just as matrix elements, something more familiar to students, for example, uh, to classify chaos, to see chaos.
Sorry. So matrix.
So why don't you study S matrix elements of S matrix? Because you basically do have a scattering problem.
I see. Yeah, it could be interesting. I guess if these OTOCs that we were computing, right, the analogy would be studying essentially the S matrix on the flat string, I guess. So we would not even be studying the AdS2 string. It's the flat string. I don't know if there's been work done on that or what it looks like. Yeah.
Okay, but you do have you can calculate the S matrix elements actually, and try to understand whether these elements indicate chaos.
So these S matrix elements, you mean for the AdS2 string?
Yeah.
I see. Maybe I can. I'm not sure if this is related to what you were saying, but one thing we wanted to understand better is, so the scattering argument we kind of recycled from some previous works, and again, I'm not. I don't know very much about this, but I know that there's this program to interpret CFT correlators as scattering amplitudes via the Malin transform, exchanging the conformally invariant cross ratios, often called UNV, for some variables S and T that behave a lot like Mandelstam variables. So I think it would be very interesting to try to understand these Wilson loop correlators as scattering amplitudes via some sort of Mellin transform. But to my understanding, I think there are some subtleties with defining the Mellin transform in one dimension. So I think that would be an interesting direction to study. In fact, one of the what we're kind of working on now is to study these 6-point functions at tree level, which allows us, which requires studying the reparametrization path integral, the reparametrization action to the next order, such that it's interacting. But one of our motivations was that if we would have this 6-point function, which could be turned into a 3-to-3 scattering amplitude, then maybe we could probe more sensitive questions, more like detailed questions about the integrability of the matrix, for the scattering matrix, for example.
Thanks.
Thank you.
Is there any, I don't know, like qualitative argument why there is a bound on chaos? And what are the theories that saturate it? Like, is there anything known about it? Like you said, like gravity, right?
Right.
And if you add something to gravity, like gravity plus scalar or something like that.
Yeah, I think any theory. My understanding is any theory with gravity with some modification would also saturate it. Right.
Which essentially means it should be like any theory, because in AdS2, I guess the bulk should contain gravity.
Yes, that's a good point. So right. So if you study bulk 4-point functions analytically continued into this out of time order configuration, you again find the maximal Lyapunov exponent. As you said, exactly because the dual theory in AdS is Einstein gravity and the supergravity regime. What is kind of so in some sense, the fact that there's maximal chaos on the string maybe was not surprising. What was kind of interesting is that the parameter that determines, so the Lyapunov exponent is the same, but the time at which the correlator deviates significantly from 1, which is sometimes called the scrambling time, is different in the bulk and on the string. In the bulk, it's set by 1 over n squared in the gauge theory, or in terms of G Newton in the bulk. Whereas on the string, it's set by 1 over the string tension. So there's maximal chaos both on the string and in the bulk, but the time that it takes to essentially scramble is faster on the string than in the bulk, which kind of also intuitively makes sense because it's a probe sector with fewer degrees of freedom.
Mm-hmm.
But yeah, maybe in some senses it was not so surprising that the string has maximal chaotic exponent, the Reparametrization exponent.
Okay, thank you. Any other questions? Okay, since we don't have any other questions, thank you for a nice talk. And
Thank you.
thank you everyone for coming, and see you next time.